In the last lecture, we saw that quantum computer is a collection of a few qubits, and we have a way of isolating those qubits from the rest of the universe, and we are able to perform control operations on them. In this lecture, I will talk about those control operations. These control operations on qubits are called quantum gates. So, in this session, I will try to give a very simple introduction to quantum gates, both for operations on single qubits, which are called single qubit quantum gates, and also two qubit quantum gate. And especially, we will focus on a very ubiquitous and important quantum gate on two qubits, which is called control X or control naught quantum gates. So let's start with single qubit quantum gates. So these quantum gates are nothing but controlled operations on qubits, and these operations and their physical implementation depends on the type of computer. For example, if we have a trapped ion or a trapped atom computers, these operations are essentially performed by if we have a trapped atom, so then the quantum gates in actuality means the photons that we are sending towards them, or maybe the lattice oscillations and the interactions through those lattice oscillations. And maybe if we have a superconducting uh, qubits in quantum computer, then these quantum operations essentially means that we are sending RF signal to these qubits, and then the qubit state is changing. So in this course, we are not going to worry too much about how these physical operations are performed. We will just be using their mathematical abstractions using uh, matrices. And since qubits, qubit states are nothing but column matrices, for example, a single qubit state is given by a column vector AB, and maybe we can choose this state to represent it in a special basis. Let's say this basis of 0 and 1, which by the way is also called computational basis, because we can encode data in it and read data in this form. In this case, 0 is nothing but this column vector 1 0, and 0 1 is this column vector state ket 1. So in this case, the quantum gate is essentially a way of transforming this matrix into another matrix. And since this is a 2 by 1 vector, this is 2 by 1 vector, this can be, for a single qubit, a matrix which is a 2 by 2 matrix. Now, the physics of the mechanism requires us that this matrix be unitary, because it then preserves the probabilities. We can actually see that why this has to be a unitary operation. And just to recall, a matrix is called unitary if its dagger is equal to its inverse. And just to recall again that the dagger means that you take the transpose you take the transpose and conjugate. So for example, if U is this matrix A, B, C, D, then U dagger would be A conjugate B conjugate, sorry, I don't know why the pen is not working. Let's say, go back again. So this D conjugate and C conjugate here and B conjugate here. So, and conjugate, again to recall, is the complex conjugate, that if we have a complex number 2 plus 3 iota, A conjugate means that we flip the sign of iota. So it becomes minus 3 iota. So a matrix is called unitary if its dagger is equal to its inverse, which means that U dagger into U is identity, or U into U dagger is also identity. That if I multiply the matrix with its dagger, I get identity. And let's see how this can help us preserve the normalization of state. So this state psi, which I wrote as AB, which I can also write as some A times 0 plus B times 1. Let's say that we apply a unitary a unitary operator on this, and we get some state psi prime. So if this is psi prime, and suppose this psi is normalized, which means that if I take the inner product of psi with itself, which essentially means that I have to dagger psi and then multiply with itself, and psi's dagger is its conjugate transpose, so this becomes A conjugate B conjugate AB, so this is A mod square plus B mod square, and this is 1 if the state is normalized. So suppose that we are given this. Let's see what happens to psi prime. So psi prime, let's find out its norm. So to find its norm, I will have to find the inner product of psi prime with itself, which means that I have to multiply psi prime's dagger with psi, and since this psi prime is given by this, so this becomes, so by the way, this is also psi prime. So psi prime is U psi dagger, and then this psi prime is again U psi. Now when I take its dagger, because these are two matrices, essentially this is a 2 by 1 matrix, this is also a matrix, so the matrix rule tells us that when we take the transpose down, the order changes. So this becomes psi dagger U dagger U psi, and this side, so this psi dagger, sorry, not psi prime, so this becomes psi, and this U dagger U is nothing but identity if this is a unitary matrix, so this is psi, so then this becomes psi, and we see that if this U is unitary, that its dagger is its own inverse, then this gives us identity. So it means that the norm of psi prime is the same as norm of psi, and since psi was normalized, so this was 1, so by operating our state with the a unitary operator, we made sure that the probabilities are conserved. So we can give this statement in general that unitary operators preserves norm, and they are like physical operators, because if the norm is not preserved, the probabilities wouldn't transform in the right way. So let's take a few examples. So suppose we want an operation, let's call it example number 1 and call it NOT gate. So we want operator which transform 0 into 1 and 1 into 0. And this is also a very important operation in terms of computation, because in many classical circuits as well quantum circuits, we need this ability to flip the state from 0 to 1 and 1 to 0. Physically, you can imagine that we can do it by sending a photon of energy which is equal to the gap of the states. But if we want to represent the process in terms of a matrix, we then have to come up with a matrix. Let's call that matrix X, which is something that when it operates on state 0, it should give us 1. And when this matrix operates on state 1, it should give us 0. Now, 0 state is 1 0 column vector and 1 state is this. So it means that this matrix X has to be such that when it is operated on this, we get 0 1, and when it is operated on this, we get 1 0. So you can easily verify that this is the matrix that can do this job. We can easily check, for example, if I apply this matrix 0 1 1 0 on state 1 0, which is equivalent to X applying on 0. So I get 0 into 1, 1 into 0, 0, 1 into 1, 0 into 0, 1 plus. So this is 0 plus 0, this is 1 plus 0, which is 0 1, so which is nothing but state 1. So similarly, we can check that when X is applied to 1, 0 1 1 0, this gives us 1 0 S0. So this is a matrix that gives us this transformation. But we also have to make sure that this matrix is unitary. And let's check if that is the case, because only unitary matrices are allowed physically. So let's take its dagger. So for its dagger, I need to take its transpose. So its transpose would be, so these diagonal elements there. So this one goes here and this one goes here. So it's the same, and there's no complex number, so conjugate doesn't play a role. Now let's check if X dagger X is identity or not. And by the way, this happens to be same as X. So this I can also write as X square, because this is X, this is X. So 0 into 0 plus 1 into 1, 1. 0 into 1 plus 1 into 0 is 0. 1 into 0 plus 0 into 1. 1 into 1 plus 0 into 0 is 1, which is identity. So it means that its dagger is indeed its inverse, because when I multiply the dagger with the matrix, I got the identity. And not only that, we can easily see that this was expected, because X square identity mean that I'm applying the gate twice. So let me just use gate notation. So we go from left to right. So this is X gate, this is X gate, and this is output. So it means that if my input was 0 and I applied this X gate 1, this input transforms to 1. And if I apply the X gate again, this input should flip back to 0. And if my starting input was 1, this X gate changes it to 0, and then another application of X gate changes it to 1 back. So applying X twice, which is X square, should be identity anyway, because the second X does sort of the same thing and flips the bits back. So this is NOT gate, or also called X gate, is one of the fundamental operation that we will be using a lot in quantum computing. This gate, by the way, is also called Pauli X gate for historical reason, because Pauli, when he was working with the spins of particles, spin half particles, he found several operators. So one of them was this X operator. So since this X operator turns out to be the same as Pauli's X operator, sometimes this is also called sigma X, or some people write it as sigma 1, and so on. But the sigma 1, sigma X, or X means the same thing. We will be adopting a simple notation which is common in quantum computing, and we will just write X instead of sigma X. Let's take another example. And let's take a Z gate. So instead of taking the Y gate next, let me take Z gate. So Z gate is a gate that changes sign. So we need a gate which does nothing to state 0 but flips the signs if input state is 1. And symbolically we can represent it like this. So the flow is from left to right. So it means that 0 state should go to 0, no change, and 1 state should go to 1 state. So first of all, let's see what the matrix for this Z gate should be. So I want a gate or a matrix which doesn't do anything to, let me just write again, just doesn't do anything to this 2 by 1 matrix 1 0, and gives a minus sign to this matrix. And we can easily verify that this matrix does the job. And let's check. So let me apply this Z to state 0. So 1 0 minus 1 1 0. So 1 into 1 plus 0 into 0 is 1. 0 into 1 plus, this is 1 plus 0. So this is 0 minus 0 is 1 0. So 0 is back. And if I apply this 0 to 1 state, this Z to 1 state, 1 0 0 minus 1, this becomes 1 into 0, 0 into 1, 0, 0 into 0, minus 1 into minus 1, minus 1, and let's take minus out, and this becomes this. So this is a gate which gives a negative phase if the input state is 1. So that's why this Z gate is sometimes also called phase flip gate. But this name is actually a little bit misleading because it doesn't always flips the phase. This is the name that is common in literature, even though I think the better name would have been selective phase flip gate, because it doesn't do anything to 0. It doesn't flips the state of 0 qubit, but it flips the phase of the sign of the one state. And maybe in one respect, this name might make sense if we try to write this 0 as exponential iota 0 into cos theta by 2 0 notation. So if we go back to that theta and phi notation, there we might make sense of this phase flip, uniform phase flip, but otherwise it's easier to remember that it flips the phase if the input state is 1, because the sign changes and does nothing to 0 state. Now let's also see if this gate is also unitary, because we always have to make sure. So for that, let's compute Z dagger. So Z dagger again is the same matrix, because this is Z, and if I take its transpose and conjugate, I get the same gate. So this is equal to itself. And by the way, these types of operators in which the dagger is equal to itself, these operators are called Hermitian operators. So this Z happened to be a Hermitian operator. Let's see if it happens to be a unitary operator. Same was the case for x. X was a unitary and a Hermitian operator. So let's multiply z dagger with z. So 1 0 0 minus 1 1 0 0 minus 1, and you can check it for yourself that it turns out to be identity. So it means that this z square is identity, which again makes sense because if we apply z twice, we should get the same input back. Because if this is state 0, z gate does nothing to it, and then another z gate does nothing to it. If this the input state is 1, z gate gives it a minus sign, and then this is 1, so this another z gate gives another minus sign, so this becomes 1 again. So z square identity makes perfect sense. All right, so this is the phase flip gate, and we had a NOT gate before this. Let's now talk about the third Pauli gate. By the way, Z was also a Pauli gate. So let's talk about Pauli Y gate. So Pauli Y gate essentially is something that in some ways combines the properties of both X and Z gates. So this is a gate. Let me start with its matrix. So its matrix is 0, minus iota, iota, 0. So first of all, it have non-zero elements on off diagonal, and it also have a different sign for both of the elements. So let's see what it does to state 0. So 0 minus I 0 into 1 0. This becomes 0 into 1. Minus iota into 0 is 0. Iota into 1 plus 0 into 0 is iota. And let's take iota common. So this becomes 0, 1. So this is iota 1. So it means that y applied to 0 goes to iota 1. So the state is flipped with a global phase iota, with a factor iota, which can actually be written as a global phase, because iota can be written as iota pi by 2, because if I open this thing, this becomes cosine pi by 2 plus iota sine pi by 2, and this is iota. So let's see what Y gate does to the other state, one state. So y applied to 1 will give us 0 minus iota, iota 0, 0, 1 is 0 into 0 minus iota, iota into 0 plus 0 into 0, this. So this is minus iota common. So it means one state has been flipped, but it has also been given a negative sign, unlike here. So this is a gate which is sort of doing both of these things together. So that's why sometimes this Y gate is also called phase flip gate. So this flips the phase, this gives a phase, and this also flips the state. So let me just give a summary, because these names we'll be using them again and again, so it's better to have a nomenclature. So X is a NOT gate, Z is a phase gate or a phase flip gate actually, and this is a NOT gate or state flip gate, and then Y is the one that flips the state and phase. So this is sometimes called phase and flip gate. So this, by the way, is sometimes only called phase. So this flip can be reserved for the Y part, and then we can also potentially think about the identity gate, which does nothing. So this actually set of 4 gates is called the Pauli gate set, and these gates are called Pauli gates. And by the way, this also forms a basis for all 2 by 2 unitary operators, that any other unitary operator can actually be written as a linear combination of these gates. So if you think of a vector space of 2 by 2 matrices, so then this forms the basis of that vector space, this IXYZ set. There are other simple bases as well, but this is a basis which is commonly used in when dealing with 2-level systems. All right, so let's go to another very simple gate, and perhaps another extremely important gate. So this is called Hadamard gate. Its symbol is H. So let me start. Actually, I didn't talk about to show if Y is a unitary matrix or not, but let's briefly quickly check it. So suppose this is the Y matrix, and then Y dagger would be, you take this here and this there, and then so this is the transpose operation, and you also have to take conjugate because dagger is 2 operations. So when I take, so this iota goes there and minus iota comes down, but when I also take the conjugate, so again the sign flips and I get this minus iota back and iota back. So this is again Y, and you can check that Y square identity will come out just like the previous operator. So all of the Pauli operators actually are like this, that their square is identity. So x square is identity, y square is identity, z square is identity. All right, so this Hadamard gate has a symbol H, and let's see its operation. So this is a gate defined by this little bit terrifying matrix at this stage, and let's see what it does. So when I apply this Hadamard to state 0, so I get 1 1 1 minus 1 1 0, 1 into 1 1 into 0 is 1, 1 into 1 minus 1 into 0 is 1, which I can write as 1 over square root 2 1 0 plus 0 1, and this is state 0 and this is state 1. And this state has a special name. We call it the plus state. We actually discussed it briefly in the last lecture as well. And then let's see, when we apply Hadamard gate to 1, what do we get? So 1 into 0, 0 into 1 is 1. 1 into 0 minus 1 into minus 1 is minus 1. And if I expand it, so this becomes 1 0 minus 0 1. So this at the end becomes this 0 minus 1. And let's label this state as 1. So basically what is happening, that the Hadamard gate actually prepares superposition states. When the input is 0 state, the output is an equal superposition of 0 and 1 with a plus sign. And when the input is 1, the output is again an equal superposition of 0 and 1, equal because they both have coefficient 1 over square root 2, but with a minus sign. So this Hadamard gate essentially prepares the equal superposition state. So this is a very important gate, because what happens that when, let's say, you have this 2-level system and your initial state is this 0 state, and you apply this Hadamard pulse, the system ends up in a superposition state. And similarly, if the starting system is in this state and you apply the Hadamard gate, system again goes into superposition state, which is different from the previous superposition state because it has a minus sign. And let's see, by the way, what happens if you apply the Hadamard gate again. Suppose I apply Hadamard gate back. So let's say if I apply Hadamard to plus state, so then mean that I have to apply Hadamard to 0 and 1. So this becomes Hadamard on 0, Hadamard on 1. And Hadamard on 0, we already know what happens. It's here. So this becomes 0 plus 1. And this we already know because this is here. This becomes 0 minus 1. And since they both have the same coefficients, we can see that this plus 1 and minus 1 cancel out. Because they have opposite sign and same coefficient. And the 0 and 0, they add up. So this coefficient is half because 1 over square root, and this outside 1 over square root is half. So half 0 and half 0 state becomes full 0 state. So we get 0 back. So when we apply Hadamard again, plus state goes to 0. Similarly, this minus state goes to 1 state back, which essentially means that Hadamard square is identity gate again. So if we apply Hadamard twice, we get identity. And I leave it as an exercise for you to check that this is a unitary gate, that when you take its dagger, which actually we just showed in a way, because this dagger would be the same gate and 8 square is identity. All right, so this is sort of an introduction of single qubit gates, and in the next few lectures we will actually go into more details of single qubit gates. But for now, let's stop there and discuss 2-qubit gates. So 2-qubit gates are gates that act on 2 qubits simultaneously. So you can either imagine that we do something to this qubit, do something to get this qubit. So that's like one way, one type of 2-qubit gate. And then we can also have a situation like this where we do something jointly to these 2 qubits. So for example, we couple these qubits in some way, and then we do an operation that change the states of these 2 qubits jointly. So when we generally mean a 2-qubit gate, that's what we are meaning. We are not saying that we are doing independently to 2 qubits something, but we are jointly doing something to the both qubits at the same time. There are many important multi-qubit gates, and we will be covering as we go on. But let's start with the simplest and the most important 2-qubit gate, which is called control X gate or control NOT gate, and we will use symbol CX for this gate. So let's start with the truth table, because truth table can help us a lot. So imagine I have 2 qubits. So there's this qubit and there's this qubit, and let's say this qubit's name is Q0 and this qubit's name is Q1. Okay, so suppose that this is the state before and this is the state after the operation. So before, these 2 qubits can be in these states. If we just think about the computational basis state. Remember, if we know what happens to the basis states due to a gate, we can work out what happens to the any arbitrary state, because any arbitrary state can be written as a sum of these states. For example, any 2-qubit state can be written as like this. So let's say I apply some gate u to this state psi. So because of linearity, so this gate gets applied to each of the individual state. So to find the output, all I have to know is what happens here, like what's the output of this term, and 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 I'll be able to find out the total output. So all we need to know is what happens to computational basis states. So suppose that we want a gate that does like this, that suppose this left side is a control qubit and the right side is the qubit where we want to perform an X gate. If the control qubit in 0 state, so this qubit, suppose that it's a 2-level system, so this is in this ground state, we don't want to do anything to the second qubit. So we want the states remain as it is, both states. And if this state is in, this qubit is in 1 state, the left qubit, we want X gate applied to the second qubit. So this is in 1. So this 0 state becomes 1 state, and this 1 state becomes 0 state. Okay, so which means that if this u is, my control X gate, so if this u is this control X that we are talking here, so then this would be 0 0, this would be 0 1, so this would be 1 1, and this would be this. So this would be psi prime state at the output. So this gate has a special symbol. So we put a dot, solid dot, and then there are two ways. Either you will see a plus sign written, or there's another equivalent symbol where we just put a box and write X. So this is the symbol for control X. An alternative symbol for this control X gate is this. Like this. So they're both equal. So this CX gate has this property. And by the way, if you want to write out the matrix for this CX gate, then we will have to work out the vector states for all of these states, and then work out which of those is going to be. And we can easily check that this matrix does the job. Sorry, let's see, I think a mistake here. So this has to be 1 here and 0 here. And we can check, let's say this 0 0 state is 1 0 0 0. So if I apply this matrix to this, so this 1 0 0 multiplied with this is 1. So 0 1 0 multiplied with this is 0. 0 0 1 is 0. 0 1 0 is 0. So I get this state back, and let's check one of these. So if the CX is applied to, let's just check the last one. So 1 1. So 1 1 state is 0 0 1. So this 1 0 0 with 0 0 1 is 0. This 0 1 0 0 with this is 0, and the 0 0 0 1 with the 0 0 0 1 will be 1, and then the 0 1 0 would be 0, and this is nothing but this state. So this is the matrix representation for this, and I leave it as an homework exercise to show that its dagger multiplied with it is a 4 by 4 identity matrix. So in a nutshell, the control X gate does a conditional operation on the second qubit based on the state of the controlling qubit. So sometimes this is called control qubit and this is called the target qubit. But this can give a misleading impression that nothing happens to the control qubit, even though it seems like in this case that nothing is happening to the control qubit. But in general, we can see that it's the joint state of the system that changes, and we can't really think that nothing happens to this state and only something happens to this state. And actually, I think let's take an example that should clarify it. Let's take a couple of examples. So example of operation of control X gates. So let's take a control X applied to 0 plus state. So which means that I have to apply control X gate to 0, 1 over 2, 0 plus 1. And before applying control X, let's just work out this thing. So this is square root 2, I can just write over here. So this 0 tensor 0 becomes 0 0, and this 0 tensor 1 becomes 0 1. So 1 over square root 2. So this control X will distribute on both terms. So control X 0 0 plus control X 0 1, and now we can see what will happen. So this control qubit is in 0, nothing happens to this. Control qubit in 0, nothing happens to this. And I can take this 0 common on the left side again. Remember this tensor always here, which is not written. I'm now explicitly writing it, and over here I'm left with this 0 and this 1. So this becomes 0, and this is again plus state. So you see, the control X gate didn't do anything to this state. So the state passed right through it. So no changes to actually anything, simply because there's a 0 on the left. And let's see another situation. So let's say Cx, example number 2, applied to 1 plus. So in this case, I can write this thing as 1 over square root 2 Cx on 1 0 plus 1 1. Remember, this plus state is this 0 plus 1, so I can distribute this 1 on both of these. And now when I apply this control X gate on this, so this is 1, so 0 flips. And now when we apply this Cx here, so this is 1, this 1 flips. And now this, on the left side is 1 state, so I can take this common again. So tensor 1 over square root 2, this is 1 plus 0, but this is same as 0 plus 1. So this is nothing but plus state again. So it means nothing happens to even 1 plus state. Okay, so because this plus state, when its individual basis states flipped, it again became a plus state. So let's take yet another example. Let's say that I have a control X applying to 1 minus state. So this would be then this is 1, and this minus state is 0 minus 1 over square root 2. So 1 over square root 2 is here. So this is 1 0. So the control X gate will make this 0 as 1, and this is 1 1. So this control X will make it 0. And now I can take this 1 common again on the left side, but on the inside we hold on, I lost connection to the screen. Okay, so this is little bit troublesome, but let's end this session here because somehow the screen isn't working. Let's see if I can get it back quickly. Otherwise we'll have to end the session. Perfect. Looks like it worked out. All right. So let's keep going. And continuing with the previous example, I was applying the CX gate to this state, and we are able to take this 1 common, and then there was 1 over square root 2, 1 minus 0. But what I can do is I can take this minus sign common. So then this becomes 0 minus 1, which is minus state. So you see the control X actually didn't flip the state. It just gave a negative sign right over here. And last but not the least important example, let's take another one. That let me apply this control X gate to minus this state. So this would be control X applied to 1 over square root 2, 0 minus 1, and this 1. So this becomes 1 over square root 2, Cx on 0 1 minus Cx on 1 1. Actually, let's do two states at the same time. So plus minus. So if the state is plus, there's a sign plus. If the state is minus, there's a sign minus. So this becomes here. So we can do actually two examples at the same time. So this 0 1 remains as it is. Nothing happens here. But this control qubit is 1. So this 1 becomes 0. So this becomes 1 0. Now you see I can't even take anything common on left and right because this 0 is here but 1 is here, and 1 is here and 0 is here. So this has transformed to a very strange state that this sort of, let me just write it in symbolically, that this control X gate has transformed plus state here and 1 here into a state 0 1 plus 1 0 and a state with minus here and 1 here into 1 over square root 2, 0, 1, minus 1, 0. Now this is a state that I can't even factor out into two parts. Like I can't write a state in terms of the left qubit and the right qubit state. So this state which was factorized, like I could write this qubit state separately and this qubit state separately. After control X, the qubit states can't even be separated from each other. So these states, they're called entangled states. Because they cannot be written as a product state of one qubit and state of the other qubit. And therefore this CX gate is sometimes called entangling gate. And we should never think that this control X gate means that one qubit is controlling and it's not changing and only the second qubit is changing. In general, this control X gate performs a joint operation on two qubits, and the state can transform in a myriad of ways. That a product state can go to an entangled state, and similarly we will see in coming lectures that the entangled state can be converted back to a product state with this thing. So with this, let me conclude this very simple introduction to quantum gates, where I try to present single qubit gate as a 2 by 2 unitary matrix and a 2 qubit gate also as sort of a 4 by 4 unitary matrix. And we saw that X gate flips the state 0 to 1, 1 to 0, and Z gate selectively flips the phase. So it flips the sign of one state and does nothing to 0 state. And Y gate essentially does both things at the same time. And the control X gate is a gate that entangles the two states if the states are in a special product state. And the Hadamard gate essentially is the one that flips the bases. We saw that a 0 state goes to plus and 1 goes to minus. So it means that 0, 1 states go to plus minus states. So plus minus is another basis, sometimes called Hadamard basis. And similarly, if we applied Hadamard gate to plus and minus state, those states go to 0 and 1 state. So the Hadamard bases or plus minus bases can be converted back to 0, 1 bases with the Hadamard gate. So in the next lecture, we will build on this simple introduction and revisit actually single qubit and 2 qubit gates and introduce outer product form, or sometimes called operator form, of these gates, which is helpful for computation, because you just saw that a control X gate was a big matrix with only a couple of non-zero entries. And if we go to then multi-qubit gates, then it becomes very difficult to write big matrices. So in place of that, we physicists have invented a simpler notation to handle operations on large number of qubits. So we will introduce that, and then also talk about more single and 2 qubit gates like rotation gates and control rotation gates. Thank you very much.